So today we have the pleasure of welcoming Daniel Shade to our Leomo webinar series. He is the driving force behind gebioMized as both the lead sports scientist and CEO. Today's webinar is focusing on developing a fast and sustainable aero position on the bike. This will involve bike fitting with both the combined technologies of gebioMized and Leomo. And then just another reminder for those who just joined, we have a few more participants coming in, to please use the Q&A section for questions. Okay, Daniel, I'm going to officially hand it over to you now.
Hello, everybody. Good evening from Germany to all of you worldwide. And first of all, thank you very much to the Leomo crew for inviting me to this webinar today. I'm pretty excited to present a little bit of my work to all of you today. And when I speak about my work, let me introduce myself just for the starting point, that you get a little bit more as an idea who's talking to you today. So my name is Daniel Shade. I'm working as a sports scientist for a company called gebioMized. We are located in Münster in Germany, and we are working in the field of cycling biomechanics since 2002. And that's basically also the starting point for me. So I've studied sports science at the university in Münster. I also wrote my master thesis about custom saddles and analyzed pressure on the saddle in an outdoor world. So this is more than 15 years ago now. But as you can see, I was, for quite a long time, I was interested in measuring outdoor, and that might be the reason why this combination of myself as a bike fitter and Leomo as a technology works in such a good way, because they also love measuring outdoor. gebioMized is a part, or was a part of a group of companies, and in 2017 we decided to split, and now we're a private company, and I'm the CEO since 2017. And since 2015, we are concentrating a lot on aero stability. That's a word that I would say we have created, and that I would like to describe a little bit today, and help you to dive into my world. And yeah, this was in 2015. I also have the pleasure to work with a lot of pro athletes over the last years, both in cycling and in triathlon. I've just give you a little bit of an overview. I'm currently working with Team Ineos, former Team Sky. I also worked with them when they were Team Sky in the last couple of seasons. And we're also supporting Mitchell & Scott as with our biomechanical consultation and aerodynamics consultation as well. And we have worked with Trek Segafredo for more than 5 years. And beside our work in the cycling world, I also worked with some of the, I would say, the best triathletes in the world. So I have helped Jan Frodeno with his position. I've worked with Sebi Kienle on some biomechanical issues, with Cameron Worth, that maybe a lot of you also know, Patrick Lange, also here located in Germany, and a female pro triathlete, Dani Bleimehl. So just a quick overview about myself and about my work, and maybe easier to get it when you look at some pictures. So I decided to bring you a few pictures that you get a little bit of an understanding how to work. So when you look at these pictures, you see there are different scenarios. So on the left-hand side, we see some or two pictures from outdoor measurements. So on the top of the left-hand side, we see Alistair Brownlee, and that was a fit session, an outdoor test we have done middle of last year, preparing for the 70.3 Worlds. And when you have a very, very close look and detailed look, you see a small piece underneath his saddle. This small piece is a Leomo Type R unit. So we have used that in the test to grab a little bit of information in terms of his position movements. And also when you look on top of his shoe, you might see one small sensor, and this is also a Leomo sensor. The picture below, this is Jan Frodeno and me when we've worked on the road in terms of saddle stability, also in outdoor testing in this picture. Then you see Cameron Worth here on top, where we've worked a little bit on his active position on the bike in preparation for Kona 2019. Here you see Sebi Kienle and me working in our lab in Münster and preparing a little bit on his position. On the right-hand side, we see an aerodynamic testing that we also do in velodromes here, and this is with one of the riders from Team Ineos. And this is a typical lab situation when we work on a stationary trainer with a triathlete like Dani Bleimel in this case, to try to measure and to try to find some optimization. So just a quick intro about me and about the work of our company. And today I would like to talk with you about some fast positions and how to make these fast positions. And I brought one thesis. And when you look at this, it might be maybe a little bit surprising for some of you, because I still hear a lot of aerodynamic experts and bike fitters speak about it's all about the front end. If you want to make an aero position faster, you have to work on the front end, you have to just reduce the frontal area, and then you're good to go. And I would say a fast position in triathlon and also in time trial always starts with a pelvis. If there's not everything's optimal around the saddle contact, then I don't think you can reach the optimal position in terms of aerodynamics. And let me try to explain why. Let's first of all define what do we mean when we talk about a fast position. For me, it's always a triangle of different aspects, and I have to balance these aspects as a biomechanist in the best possible way. And the best possible way is always an individual way. So it's not that everybody has the same answer and that you need the same approach and the same adjustments and the same tools for every rider. You have to find your individual way. And this is always a balance. You have to balance comfort and stability on one hand. So somebody has to feel comfortable, especially when you work with age groupers and they sit on the bike for quite a long time, or yourself. You plan to do an Ironman, for example, and you have to sit on your tri bike for hours, then comfort and stability plays an important role. But it's also about power transfer. You have to balance that, because you still want to push the pedal as hard as possible, but also as efficient as possible. You don't want to lose a lot of power just because of sheer forces and because of some issues in your power transfer. And then, of course, we're talking about aero, so aerodynamics is also a topic we have to care about. So it's not being as huge as possible in front of the air. It's also how can we hide in front of the wind, for sure. But as I said, it's always a balance. If you can create a good comfort and stability scenario, it's really hard to find the optimal aerodynamics. If you don't have the right power transfer, then the best aerodynamics doesn't help a lot. Maybe a little bit, but not a lot. And today I would like to talk about the approach, how to use the gebioMized pressure mapping system and the Leomo IMU system to find some answers for yourself when you're an athlete, or for your clients when you're a bike fitter or coach, for example. And for me, the main thing is how to measure these aspects. How can I measure power transfer, aerodynamics, and comfort and stability? And the last two are green because these are my two topics for today. I would like to show you how we measure comfort, how we evaluate stability, and how we put that together to find some fit answers for my clients, for my riders, for my pro athletes. Before I show you a few cases out of that world, let's talk a little bit about contact points. So when we see an aero position like this, we always have 3 contact points. We have a foot pedal interface, we have the pelvis sitting on the saddle, and then we have got the arm pads here in the front and the cockpit as a 3rd contact point. You always have to keep in mind all these contact points interact with each other. So when you do an adjustment to your foot pedal interface, for example, by making a change of your cleat position, longitudinal, more to the back, then you influence your seat height. If you rotate your cleat, for example, then you might have an influence to your knee that might influence the pelvis, and then it's also an influence to your contact point saddle. If you change your arm pad position in here, it might have an influence to your saddle. It might have an influence to the way that you're sitting on the saddle with your pelvis. But also if you change something around the pelvis, for example, a different saddle model or different seat height or whatever, there is an interaction to your armpits. There is an interaction to the way that you push the pedals with both feet or that your knee is moving. So I think it's important to understand and to accept that there is an interaction between all contact points. And we always have to keep in mind, if we make one change, there might be an effect at a different contact point. And the fit questions we are always asking are these four. What about comfort? If you feel comfortable with your pelvis because a significant amount of body weight is connected to the saddle and the saddle gives you a large contact area and not so much pressure, then it's quite high. There's a quite high chance that you also have a good stability of your position, that you don't have to move very much with your pelvis, because when you start moving, then you might have an interaction with your shoulders. If the pelvis moves a lot lateral, left and right, then the shoulders also might follow and you might have a lateral movement left and right too, maybe even stronger because there's a lever coming from the pelvis through the back to your shoulder area. So comfort, stability, lateral movements, and this is valid for all contact points. And then it's also about weight distribution. How do you distribute your body weight over the three contact points? Are you sitting completely loading the saddle, or are you sitting balanced between saddle and aero pads, for example? Or are you sitting front loaded, that you bring a lot of your body weight to the arm pads? This also might result into an unstable position because you start moving with your shoulders, you start to compensate because you're not feeling comfortable with your shoulders. So we have to keep in mind. And as I said before, it's important to know how to measure. And we have got two technologies that we can use to measure the contact point saddle. And this is my first starting point because, as I said, the pelvis is a starting point if you want to create a fast position. This is an example of one pressure plot on the saddle. You see that in a typical tri position or aero position, you have a lot of pressure in the front. This is colored in red here and in yellow. And then you have got a little bit of pressure in the midsection of the saddle. And then you have got basically no pressure at the rear part of the saddle. This is given because of that balance in an aero position between front end and saddle. If we want to optimize comfort for a position, then we have to objectify and we have to measure what's going on between pelvis and saddle, because that allows us to look at this contact point and to make it better, to find some room for optimization. And we're using the technology pressure mapping. This is the gebioMized system that you can see over here. And then we have got a few parameters that we can use to look at. For example, maximum pressure. This is correlated to comfort. So if we see that number here, 1250, it tells me it's not the best comfort I can imagine for this rider. So what do? I try to make a few adjustments from a bike fit perspective. Then I make a remeasurement and see, can I reduce this maximum pressure value? It's also about contact area, because pressure is force divided by area. If I want to reduce maximum pressure, I could also increase contact area. The rider can sit on a larger area and that reduces maximum pressure. And then I look at the center of pressure to get an understanding how the pelvis is moving on the saddle. Do I have any kind of limit on one side in terms of the other side, so I can get a better picture how the pelvis is moving? And this also helps me to find an answer about the balance between loading and unloading. If you load the one saddle spot for all the time in 100% of the pedal stroke, there's a high risk that you're feeling uncomfortable after just a short time. If you have a good balance between load and unload, then there's a good chance that you can sit on that saddle for a longer time without feeling serious discomfort. So this is one hand. This is comfort, and this is the contact to the saddle. But there's something missing in that piece, and that missing piece is the posture of the pelvis. I don't know exactly if this is a very anterior rotated, tilted pelvis, if this is a rocking pelvis, so what's about the posture of the pelvis? And to put that into account, we use the Leomo IMU sensors. So that's the combination we're looking at. We can analyze the contact point and get an objective value for comfort, but we also get an objective value for stability, because we know what's the pelvic angle. Is that a very aggressive position in terms of the pelvis, or is it a limited position? Is it maybe an upright position of the pelvis? So that's something given in pelvic angle. And then we correlate the different parameters to each other. So we understand that pelvic rock has got an influence with center of pressure. There is a correlation. Also rotation works together with the pattern of the center of pressure. And one important piece that I really like is the trend over time. And that's a missing piece when you look at bike fit technology these days, because most of the measurements you do are in the lab. It's hard to bring them outside. But by adding the Leomo technology, it's possible for us to just let the rider ride for a longer time, maybe an hour or 2 hours, and look at the trend over time. How does the pelvic angle changes over time when I have the first 5 minutes as a first stage, and then I look after 10 minutes, 20, maybe after an hour? How does that change? And these changes, this trend over time, helps me to make fit decisions that I cannot do when I just concentrate on my indoor measurements in the lab. So I hope you get an idea why these two systems, why this approach of looking at the contact point and looking at the posture is really helpful to increase stability around the contact point saddle. And here is one case study made in the real world with one professional athlete. On the left side, you see the baseline measurement. That's a baseline measurement I've described before. So a lot of pressure in the front part of the saddle and located just at a few spots. So here you see in red the maximum pressure spot. And when you look at the value is 1250, and the COP position, this describes the distance of the COP to the tip of the saddle. So we also know that this rider sits very much in front of the saddle, just 2.5 centimeters behind the saddle tip. That's really just the first 3 centimeters, I would say, that he loads most of the time. And he rides that position with a pelvic angle of 36 degrees. So what have we done? This is our baseline, and he also told us that there are some serious discomfort issues that he has when he rides for 30 minutes or more. So we tried to switch to a different saddle. This was the Stride S saddle that we have brought to the market last year. And the first thing that you can see when you look at these two measurements is there is no red inside. So here we've got a lot of red in the front part, and here we don't have any red in the front part. The whole saddle pressure is moved a little bit more to the back, and it's 50% less maximum pressure. There is no other change than one saddle model to the other. And this is just one important take-home message for all of you. If you don't sit comfortable on your saddle, if you sit on your saddle like in the left picture, then you can't reach your aerodynamic goals, because you will experience that discomfort, and this discomfort will lead to some compensation movements. You will move around, you might have a saddle shift, that you move back on the saddle, that you move back to the left or to the right, that you just jump around on that saddle. And a missing saddle stability cannot really help when you want to make your front end, for example, more aerodynamic. So make sure that you really experience comfort on the saddle. That's totally helpful. And in that case, it was our game changer for that whole position, because 50% less maximum pressure, a COP position, so a movement of the contact area about 4 centimeters to the back. So we are now around 65 millimeter, and with the same pelvic angle. And that's important, and that's something we have to control. If we just concentrate on pressure, we don't know if it's just an posterior movement of the pelvis on the right-hand side. That would mean, okay, the pelvis posture changed. It's not that the saddle is really better. It's more like, okay, he's sitting in a different way. But if we control and see the pelvic angle is in the same ballpark and we have got not even 1 degree of a difference, then we know, okay, the pelvis is positioned exactly in the same angle, but we have this benefit just coming from that saddle model. So we can think about, okay, how we can use this comfort to create more stability also to the front end. And this is just one picture or two pictures from our saddle that we have developed. And I just want to explain that in triathlon, there are two categories of loading position on a saddle. And the first one is this first part here. It's the first 6 centimeters, I would say. This is something we call the aero-position. When you want to get the last out of your aerodynamics, then you often sit in front of the saddle. And that's okay, that's totally fine, but you have to make sure that you have got enough leg clearance, for example. If your saddle is too wide and you're sitting here in the front of the saddle, then it's often that you're getting pushed forward and then you lose contact to the saddle. And losing contact means getting instable. So if you're sitting in that really aerodynamic position on the saddle, make sure that here is the right width for the saddle. And it shouldn't be too wide, but it shouldn't also be too narrow because you need contact area. If you're just sitting on one spot and you put maybe 30% of your body weight on that spot, you will also experience saddle discomfort. So make sure that this balance between leg clearance and contact area works for you as an individual rider or also as a bike fitter. Make sure that this works for your client. And then we've got a second position. This is, I call that the biomechanics position on a tri-saddle. And this is the area between 6 centimeters and 10, 11 centimeters. So the rear part of the saddle knows. If you're sitting here, then it's important that you experience a better comfort, because in that part, you do not want to tilt with your pelvis forward as much as you can, but you want to have a larger contact area, still enough leg clearance, but it's mainly about comfort. And when you work with a client and he wants to do an Ironman, but he's not sure if he can stay 95% of the whole bike split in his aero position, then try to concentrate on comfort first. Then comfort should be the focus. If you just have maybe 70% of your bike split in the aero position and the rest 30% is in the base bar, then there's nothing to gain in terms of aerodynamics. You don't have to care about a helmet or about the last spacer. Care about getting more comfort and reduce the 30% of base bar riding. This is the biggest gain you can get. And this is really connected to comfort and stability. And then it's also about the right saddle when it comes to densities, for example. For us, it was clear when we made that development, we have got more sensitive triathletes, and we also have got some triathletes neutral to pressure. And therefore, we decided to make the same saddle in different densities. So you can get the stride in a 50 shore, in a soft density, and also in a neutral density. And this doesn't mean you all have to buy the stride tomorrow, but it means care about an individual solution for your saddle, because the saddle is an aero tool, and the saddle is an aero equipment piece of your whole bike. And let me explain why, because this is another case study, and this is not about having the saddle for a better comfort. This is about taking the right saddle for being more aero. And look at this picture on the left side. You see pressure is quite okay. It's about 900 millibar. We don't see any red spots. This is our baseline measurement. The center of pressure is a little bit orientated to the right-hand side, but not significantly and not drastic. This rider came to us without a serious saddle discomfort, but he wanted to work on his aerodynamics. So he wanted to see if there is something to gain and to benefit from. And so we made a comparison. It's also two different saddles that we compare to each other here. And you see, when we just look at pressure, sorry, there is not such a big difference like in the first example. It's not that it's 50% reduced. It's basically in the same area. We've got 880 and now it's 720. Yeah, there is a benefit in terms of comfort, but not a huge benefit. But it's not so important because there is an aero benefit inside. If you look at the two lines here, you see pelvic angle range. This is minimum and maximum measured with the Leomo system. And you see in the baseline measurement, we had 33 degree of pelvic angle and maximum is 39. So this is the range that we have measured. In this second measurement, without any advice to the rider to make something different with his pelvis, we have a different range now. He's getting lower with his pelvis. He's able to rotate the pelvis more anterior and in a range that might be interesting because it's even more than 5 degrees. So we've got 31 as a minimum and 34 as a maximum. And in this case, our pressure mapping system tells us, yeah, that's fine. We don't have a negative aspect to comfort. We have at least a little bit of a positive aspect to comfort, but it's even more important to say there is something to gain in terms of pelvic tilt because he feels better when he can tilt forward. And then we can, if he straightens his back, we have some things that we can do with his cockpit to maybe go lower with the front end. So it starts here with the saddle to get him more lower on the bike. And here are the IMU data that I would like to show. So what happens is, this is the pelvis in a lateral view. So from the side, the pelvis moves forward. So the rider rotates a little bit more to the front part of the saddle because he feels comfortable with doing it. And then we have got an average difference of more than 3 degrees. This is, for me, this is huge because it opens some doors for working on the front end. And we also have less pelvic rotation, so a win in stability. And we also have a win in torso angle. So he tilts the pelvis forward and he also goes lower with the torso just by changing the saddle. There's no other thing that we have done. It's just a natural movement of the body after getting more comfort on the saddle. All the other values are quite neutral, so I would like to concentrate on these ones. And I hope that you also get an idea why the saddle might be an important factor if you just want to be more aero on the bike. And to close that part of the whole pelvis topic, I would like to give you a few take-home messages. Because we often experience some limiting factors that riders come to us with a wish of, yeah, I would like to reduce my CDA, I would like to work on a more aerodynamic position. And then they're not quite sure why it's not possible. And here are some common limiting factors that you might take and ask yourself if something might be worth to look at in your own position or in your position of some of your clients. So first of all, I've talked about that. It might be the wrong saddle, and that's also connected to the wrong saddle position. Sometimes it's not the model is just positioned in the wrong way. And when I speak about position, I mean the XY position of the saddle, and I mean the saddle tilt, saddle tilt. Because if the saddle is tilted in the wrong way, that might also limit your anterior tilt of the pelvis. But it might be that the equipment is not a problem. It's a right saddle and it's also a right saddle position, but you're still not able to move forward or to rotate forward. So it might be you as a rider. And it might be your limited flexibility of the posterior chain. It might be that your hamstrings, that your calves, that the lower back is just not flexible enough that you can rotate forward with your pelvis. And that's an easy thing that you can do, all of you at home, if you're just standing and try to rotate your pelvis forward with a straight back. Do you feel any tension in the posterior chain? That might be a sign that you can work on that you can increase your flexibility. And I also realized that there is often a missing awareness about the body and where the body is located on the bike. What happens when I try to tilt the pelvis forward? Do I really do that in the right way? Am I able to tilt the pelvis forward, or is it more a movement I do with my lower back, for example? So training awareness might be a helpful tool, because all that I explained today is about a process. There is rarely a situation where we do one change and then this works directly. You often need a time of adaptation to get used to that, to get used to new material or to new position. And it's always a positive aspect if you are aware about where the body is on the bike. And this is something that I also realized with pro athletes. It doesn't mean that you're competing at the highest level, that you have got the best awareness about yourself on the bike. And then, of course, it can also be the overall bike setup. If you're sitting too aggressive, if the drop is just too aggressive between saddle and handlebar, this might also limit your stability on the saddle. And this might result into a larger instability than necessary. And this is something I would like to explain in the second part of my presentation. So to summarize that, there are a lot of factors that might limit your aero stability. If you measure that, then you know where are the limitations. And if you know the limitations, there is a good chance that you can optimize these limitations. And I'm a big fan of objectifying positions, and this helped me a lot in the past to make fit decisions. And in that combination of analyzing posture and contact points, it's definitely one tool that, or one toolbox that brings you to better decisions. So I would like to move a little bit away from the pelvis and coming to the front end and speaking a little bit about the shoulders and why I think that a sustainable aero position also needs support for the shoulders. Because I said that the saddle carries a significant amount of body weight, and another significant amount of body weight is normally carried by both arm pads. And they are also responsible for creating support and stability in the front part. So I've just brought you two pictures that you can look a little bit to this position and let it sink in. So when I speak about the front end, I speak about the upper back, I speak about the shoulder area, about the vector of force coming from the shoulder part into the arm pad. And then it's about the elbow angle and also about the forearm to the hand. So this is all the contact or the parts involved from a body perspective into the front end. And you can look from a lateral view, or you can look from a frontal view. What do we want to see? We want to see, in an ideal world, an upper body that doesn't move significantly between left and right, because every movement to the left and every movement to the right creates a turbulence around the shoulders, and this turbulence is negative for your CDA value. So if you try to be as stable as possible here, that might be positive for aerodynamics. But of course, how can you realize that? Because you said, yeah, but at some point my lower arm just feels uncomfortable. I don't feel that I can hold that position for a long time. Yeah, totally possible. So thinking about the front end is also about the same principles and the same balance I've talked about before. So it's comfort and stability on one hand, and then it's aerodynamics on the other hand. And you have to find that right balance between the two pillars. And how to create front end stability, it's also the same principle like with a saddle. We have to measure what's going on in that position, and then we can decide where to work on. If there's something is going on with comfort, if there's comfort missing, we can work on comfort. So we can look at the gebioMized data to look at arm pad pressure, for example, and to say, oh, we see some hot spots here in red. There are high values, maybe on one side more than on the other. Let's try to reduce this high pressure spot. It's also about contact area. Do we see that the rider is just in contact with a very small area of the arm pad? Let's try to optimize that. Let's try to increase contact area. The principle is the same. Pressure is force divided by area. It's not just for the saddle, it's also for the arm pads. And COP movements are also an interesting factor when it comes to arm pads, because when you see lateral movements, they are often connected to the movements of the shoulder. So when we see a significant movement of both shoulders to left and right, we know that there is an influence to your CDA because you create these kind of turbulences. And then we put together these pressure data with the Leomo MPI, and we look at torso angle, absolute number for a quick session, but also over time. Is there a trend that the torso angle might change? Do you have to raise up your torso, maybe after 10 minutes or after 30 minutes? Then it's a typical sign for us. You're not able to hold that position. You're not able to hold that torso angle. We also look at a different parameter called torso angle in relation to pelvic angle, because when we see this relation changes, we understand there is a bending going on in the back. So for example, if the pelvic angle increases with a stable torso angle, then you often get a bending in the lower back. So it's a relation that helps us to understand the direction of two sensors and what's going on in the middle of these two sensors. And then it's another parameter over time, which is torso rock. So left and right movements also show us that there is something not optimal. And this might be related back to the pelvis, because, for example, when your hip angle is too closed, it's quite often that you do some compensation movements. And one compensation movement could be that you move a little bit with your torso to the other side, and then you can get rid of this closed hip angle in the top dead center. So interesting parameter, especially looking at this over a longer time. And this is the line here is valid for the arm pads itself. And then we've got the pelvis, because if we want to increase front end stability, we can't ignore the pelvis. So we look at pelvic angle, we look at pelvic rock and pelvic rotation. Every time when we do an adjustment around the cockpit, then we look how this influenced your contact to the saddle, because we always want to make sure that this link between upper body and the legs is not affected in a negative way. So maybe I've said it too much now, but really the pelvis is the important factor for us here. And if we bring both together, then it's even better, because then the fit decision gets stronger to say, okay, we see a high chance that pressure is better on the saddle, that arm pad pressure is getting better. So we increase that way to front end stability. And here the same path. Pelvic angle is more in that direction we want to have it. Torso rock, torso angle gets better. So we see a good chance that there is a higher front end stability than before. And I would like to show you one case study about how low is too low, because this is still a topic that we have to discuss quite often. So riders come to us with the expectation, try to make me as fast as possible. So try to make me as low as possible in the front end. But this approach often does not work. And here might be one example to show you why. So this is the baseline measurement we have measured on both arm pads. When you look on the left side, you see the pressure distributed in the middle of the arm pad, and on the right side as well. On the right side, there's a little bit larger area. But the main important factor is looking at this small piece here, which is the center of pressure. And you see that this center of pressure moves forward and backward, longitudinal, and we don't see a lot of lateral movements on the left side. On the right side, it's a little bit different. We don't see a lot of longitudinal movements, but we see a little bit more lateral movements. So analyzing the baseline, we know the right shoulder is moving more to left and right, and the left shoulder is moving more to the front and back. Okay? This baseline was measured with a drop of 16 centimeter. And then we have increased that drop because the client asked for being lower in the front end. So we did a drop of 18 centimeter, so 2 centimeter more. We reduced one spacer. And this is a result afterwards. So just one adjustment, 2 centimeter more drop. And you hopefully see that increase in that black pattern over here, that increase in center of pressure. On the left side, longitudinal, but also transversal. So you see that basically the whole area of that pattern is way larger than it was before. And the same on the right side, you see that it's larger and larger, and that this whole pattern of shoulder movements lateral are just getting worse. So this is our result we have done in the lab. And then we took the chance with that case to also take it to the velodrome and to make some CDA measurements. And let's have a look into the data analysis step by step. So these are the numbers. When we look at center of pressure, this is our first parameter. So the central point of pressure that I've explained before, transversal as an average value on the between left and right, we have 13.5 millimeter of movement transversal with the first drop. When we lowered the front end of 2 centimeter, this increased from 13 to 33. So more than double the value. COP ratio is a parameter for us to understand the area, the total area, transversal and longitudinal together as an average value. So you see this number was a very nice value of 1.6. This is something that we really call as a good stability on the arm pads. By going 2 centimeter lower, we increase that to 10. So it's more than 6 times the value. And then we're looking at the Leomo numbers. We see a torso angle, which is 9.3, and this is now 8.5. And the torso rock, which is 4.2, and now it's 6.4. So more rocking with the torso. And we have not even one degree of torso angle. So the torso is basically in the same area, but the rider has to work a lot more. That's the answer we see here in that drastic change. 6 times higher COP ratio. He has to work much, much more to hold that position and to keep that position. And then we took it to the track. And then you have got a CDA number that you can measure, which is a watt saving of 3 watts at 40 km per hour, which is for me really a very, very small difference. So when you look at this whole picture, we would say the expectation that going lower with the front end results into an aerodynamic advantage. Yeah, it's true on one hand, but it's a very, very small advantage. And there is a large disadvantage in terms of stability because of that increase in COP transversal, COP ratio, and not even a win in torso angle. So when I think about a triathlete who wants to compete in an Ironman, I would definitely go back to 16 centimeter drop because I know that this position is so tiring for him that he gets fatigued way faster. And I have to care about the run split too. So I have to make sure that he's not going off the bike and saying, okay, I'm done for today. I can't run anymore. So for me, the balance between aerodynamics, so watt saving here, and stability is definitely wrong in that case when I go to drop 18. For me, it's totally clear to say, let's go back to 16. Let's take the sustainability of 16 and the nice shoulder position and shoulder movements we had and not invest so much of energy just for 3 watts. And as a last quick summary in terms of the cockpit also, I wanted to give you some limiting factors that we see regularly in our lab. And one is the example that I've shown you before. So it's a very extreme setup, very narrow pads, very extreme drop. These are the 2 ones that we see from time to time with the expectation, okay, this makes me more aero. It often makes you more unstable and less aero over time. So it might be one fixed number that shows you, okay, when I just do this position for 1 minute, then I'm more aero. But when you think about aero over time, then it's definitely a negative aspect. So we often rebuild position to less extreme positions to make them more sustainable. And then we often see small contact area on the pads that somebody's just loading the front part, and it's also a question of tilting the pads. So I don't want to dig into the details here, but tilting the pad can be a nice idea if your lower arm is also tilted, because that normally helps to increase contact area on the pads, and then you can sink in a little bit more in the pads and have more force, more part of the body weight carried by the arm pad. And it can also be the same topic like on the saddle. It can be a limitation in shoulder flexibility, in upper back flexibility, and flexibility around your neck area if you want to go into an active head position, for example. So this is also something to consider. And don't forget, we speak about an interaction. So it might be that you're just not flexible enough around your pelvis area. And then you try a lot with your front end, but it's not the upper body. It's not your head, it's not your neck, it's the pelvis. So think about it in a holistic approach, and about your whole body and about possible limitations at different body regions. And last but not least, it can also be equipment related. So we have seen the wrong pad shape. We have seen pads that have screws underneath the pads, and the foam of the pads is just not thick enough. So you get in contact with the screws, with the head of the screws. And this is also an uncomfortable situation after a little bit of time. This could be one reason, or that there is no lateral support from the pad, for example, and that you don't have the right stability given by the equipment. It can be the wrong helmet, that a helmet forces you into a specific position, but also another topic that easily fills in another webinar, and I don't want to open that topic today. To close that area around the cockpit, it's the same principle. It's always an advantage if you can measure exactly what's going on, because then it's easier to know the limitation that really blocks you from your best aerodynamic position. And if you know the limitation, then it's way easier for you as a rider, or also for your bike fitter, to work and optimize this contact point and to find some improvements, especially for stability. And this is my last piece before I open up the question and answer round. What I've learned over the last years working with pros and age groupers is one of the most benefits and gains we can get is from optimizing and increasing stability. It's very often that you work on comfort and stability, and this results in a direct way into an aerodynamic benefit, because the person is just more quiet and stable on the bike. And this is very often the huge improvement we do in our aero tests. Okay, thank you. Thanks a lot for listening.